All right, so at this point, you should have a pretty good understanding of binary search, and hopefully you appreciate how much faster it is for large lists, sorted arrays, really. In this lecture, we're going to introduce a very useful and popular data structure called binary search tree. Okay? As the name suggests, this data structure leverages the idea of binary searching, basically uses a binary search to look up information. But the underlying structure, the actual way the data is stored and so forth, is really quite different. In the first place, it's not an array. Okay? When we were doing binary searching, we were searching arrays. Okay? So instead, binary search tree involves dynamically allocated nodes similar to linked list. Okay? The way in which nodes get linked together is completely different than with linked lists, and in fact, again, as the name suggests, the way this will be structured will be basically like a binary tree. So why do we have a need for a binary search tree? What was wrong with binary search? Okay, well, the answer is really quite simple. Binary search is perfectly fine if you sort an array and you keep it sorted, but there's a difficulty with that, particularly when you come along and add new entries to the array. Okay, if you didn't care about keeping the array sorted, then you could just add your new entry at the end of the array. Assuming you have enough room reserved, you could just lay the data in sequentially into an array. But, you know, that's no good for binary search. You have to have a sorted array. So every time you insert with a binary search array, you'll need to basically sort it. And you know, the simplest thing to do is basically do like we did with insertion sort, just shift some stuff over to make room for the new entry. In any case, that's tedious and time-consuming. It's time-consuming, really. Okay? Okay, so let's consider if we had an array of people, and we were going to add a new record, a new entry to our array of people. Okay, the person's name is Fearless Leader. So what would you have to do? You wanted to insert that. Well, first thing you do is you go through the array doing a binary search to try to find and see if Fearless Leader is already in the array. Okay? And once you discover that it's not in the array yet, then at least you'll have figured out where it belongs in the array. Okay? And as I said earlier, at that point, you can proceed like we did with insertion sort. Well, similar in some way anyway. You could shift entries to the right. Okay, starting at the spot where the new entry belongs, we could shift that entry and all the entries beyond it one position to the right. But as I said, that's very time-consuming. Imagine, you know, this doesn't matter if we're dealing with arrays of tens or hundreds of entries, but imagine that we're dealing with an array of millions or even billions of entries. Okay, then all this shifting is very expensive, very inefficient. Okay, and in the worst case, it's linear time, right? Imagine that you decide you have to insert a new entry at the beginning of the array. Then every single entry in that array is going to have to be shifted to the right. Okay, in a little while, after we reach a certain point of developing a sense of what binary search trees are all about, you know, how they're structured, how the data is maintained, and so forth, it'll become apparent that a lookup in a binary search tree is really quite similar to doing a binary search, an array-based binary search, okay? And so, not surprisingly, a lookup in a binary search tree is going to generally take logarithmic time. But the thing that we'll hopefully appreciate, hopefully you'll see that the binary search tree is a huge advantage over the array-based binary search in that inserting new data into a binary search tree also takes logarithmic time. And I'll put a little caveat in here. There's a notion of balance, and to be technically correct, it has to be said that we're really speaking about, on average, in the case of pretty well balanced binary search trees. Okay, but leave aside. Don't worry technically right now. Take it for granted right now. The big selling point of a binary search tree is that we'll be able to insert data in logarithmic time. Okay? And an important part of why we're going to be able to pull this off is the fact that the new data is inserted by using dynamic memory allocation and to create a new node, and that new node gets linked into the binary search tree. Okay? Just linking nodes together, though, by itself is not sufficient to get that logarithmic time behavior that we're after. Because if you think about it, a linked list certainly has nodes linked together, but searching through a linked list takes linear time because you always have to search it sequentially. Okay, but we're not going to think about linked lists anymore. We're trying to build binary search trees, and we'll get this nice logarithmic time behavior, as we'll see. These nodes are going to be linked together, as we've said, in such a way to form a binary tree. Okay, and if you remember, a binary tree is a situation where every node in a binary tree can have two child nodes. It can have a left child node. It might or might not have a left child node, and similarly, it might or might have a right child node. Okay? So the nodes that we're going to build here are going to contain two pointers, a left child pointer and a right child pointer. Okay? Naturally, if either of these pointers is null, then it's understood that that pointer is not pointing to a child, so that node doesn't have that type of child, right? If a node has a null right child pointer, then that means that does not have a right child. Okay, so where did we first encounter this idea of a binary tree? Well, I hope you remember. I hope you can think back and recall what we did with heaps. Yeah? We introduced the idea of a binary tree when we talked about heaps, when we developed heaps, and we introduced algorithms for heaps. Having said that, it's good if you remember heaps and you remember binary trees in heaps. But there's a big danger here, okay? Because the way in which heaps are fundamentally structured is radically different than the way in which a binary search tree is structured. And that's true in a couple respects. But right now, just at the level of a binary tree, the big difference is this. If you remember, what we called a heap was really just an array, right? The array that we used for heap, we conceptualized it as a binary tree, right? The entries in the array became nodes in a binary tree, but the binary tree was simply a conceptualization, something that we did on paper, if you like. Yeah? All right. But things are very different. Things are very different here with binary search trees. Yeah? Because the nodes that we have really are going to be linked together. First of all, with a binary search tree, we absolutely are not dealing with arrays, right? This is much more like a linked list in that we have nodes and they're linked together. And there's no array anywhere in sight here, okay? And, you know, so we're actually going to link these nodes together and really produce a binary tree, but in a very different sense than we had with heaps. We come now to another crucial difference between the binary search trees and the binary trees that we use for heaps. And that concerns the, you know, ordering of the data. How the data is ordered is very, very different. Okay? And while I don't really want to dwell on heaps, in a second we're going to forget all about heaps and never mention them again. But just to remind you, in the case of heaps, we had an ordering relation, an ordering criterion imposed that stated that in any parent-child relationship, the parent's value had to be at least as big as the child's value. Okay, and that was true of a left child or a right child. Didn't matter. Okay? All right, now forget about heaps. Never again. Not while we're talking about binary search trees. Okay? The rules are very, very different for binary search tree. Okay? In fact, binary search trees treat left child nodes in a manner that's quite different than the way in which the right child nodes are treated. In fact, they're basically treated in the opposite way. In order to carefully explain how the rules work for ordering data in a binary search tree, it's really extremely helpful to have a notion of a left descendant and also a right descendant. Okay? And these are not complicated ideas. A left descendant basically generalizes the idea of a left child, and a right descendant generalizes the idea of a right child. I'm going to do my best to explain it right here, but if you don't quite get it now, in a few seconds, a minute or so, a couple minutes, we'll be looking at examples, and it'll be very clear from the diagrams what we're talking about here. Okay, so if we start with a given node, if that given node has a left child, then that left child is also a left descendant. Okay? But maybe that left child also has child nodes of its own. Okay? Any such nodes, you know, that basically come underneath the left child would also be left descendants of the original node. Okay? Think of the given node here as the node at the top. It has a left child. That child may have itself might have child nodes, and those child nodes might have other child nodes and so forth. All of those would be left descendants of the original node. Okay? And of course, the idea for a right descendant is, is exactly similar. So if a given node has a right child, then that right child is said to be a right descendant. And if that child has any other, if there are any other nodes underneath that right child, child nodes of that right child, or, grandchild nodes and so forth, all of those nodes that come underneath the right child would also be said to be right descendants of the original node. We're now ready to state precisely what the order rules are for the data in a binary search tree. Okay? We'll assume that each node has a unique key attribute and that we're sorting the data based on this key attribute. So, for example, if we were maintaining student records again, then we could use social security number or student ID number. Student ID number would be a suitable key attribute. And we'd be able to order the students based on student ID numbers. Okay. So now the rules are very, very simple now that we understand what left descendant and right descendant are. Okay? They really are just these two criteria for ordering the data in a binary search tree to keep it valid. Okay. Each node must have a key attribute that is greater than all of the key attributes of all of its left descendants. Okay? And similarly, each node's key attribute has to always be less than the key attributes of all its right descendants. What we should do here is paraphrase these two rules a little bit and basically say this. All of the left descendants of a node must come before that node, and all of the right descendants must come after that node, okay, in terms of the key attribute ordering. I want to point out that there were some extra conditions when we discussed heaps that we referred to as extra heap conditions. Absolutely none of that applies here, so forget it. I said we weren't going to talk about heaps anymore. Well, I'm only bringing it up again to say that we don't have to worry about those complications that we had in heaps. Okay? Binary search trees are pretty much as described up to this point. Organized as nodes with pointers, and we have left child, we have right child, and we have rules concerning the ordering of the data, okay, that we just discussed. And that's it. That's all that's required. Okay, so in particular, a node might have, a left child and a right child, or it might have only a left child, or it might have only a right child. Okay, unlike with heaps, it's possible for a node to have a right child but not have a left child. That's absolutely permitted here with binary search trees. Okay, and of course a node might have no child nodes. So hopefully that's resonating with you just as I described it above, but no doubt some simple examples will help to reinforce the idea, solidify it in your head. Hopefully this next slide will do that. Rather than thinking about complex data like student records, let's stick to something. Let's assume we're maintaining a binary search tree of integer values, right? And so these integer values serve as the key attribute. It's the only data in each node, okay? So here's the picture I have in mind.